Thanks everyone for being here, and apologies again for the technical difficulties with the start time. We're just going to start now and proceed with the original schedule, planning to go over by about 20 minutes. So just accordingly, and I'll keep letting people in as they arrive. So we're delighted to have an amazing lineup of speakers for the cognitive AI benchmarking workshop. And we're recording these videos so that we can play them back at the in-person components for those that couldn't be there today. So our first speaker is Linzen.
Right, okay, yeah, I'll do it. So there's a lot that can fall under this general title of cognitive evaluation for language model. Talk about this is a form of evaluation that I think has been very important in linguistics and cognitive science, and maybe for a while at least was more overlooked in the evaluation of language models. So I'll talk about that first, and then I'll talk about evaluating whether the system produces the same responses as a human does in an experiment. So those things are not exactly the same. I'll maybe manage to convey why. Okay, so the focus on generalization in linguistics and cognitive science is based on the fact that we have a relatively limited exposure to language when we learn it, and yet we show consistent judgments about the acceptability of sentences with structures that we've never seen before, and we're able to produce sentences that are not directly similar in structure to any of the sentences that we have seen before. We have this ability to generalize composed new complex sentences from simpler sentences that we've seen before. So this is one of the most classic examples of that from Chomsky's work. We, in English, we form a question by moving the auxiliary that corresponds to the main verb of the sentence to the beginning of the sentence. It's like the simple example. Does the zebra chuckle here? And what Chomsky pointed out is that if you've only seen simple sentences like this in your training, you might conclude that questions are formed in English based on one of two rules or even more. So one rule is the correct one, where you take the main verb and move it to the beginning of the sentence. And another rule is a linear rule, where you just like scan the sentence from left to right, find the first auxiliary and move that to the beginning of the sentence. And both of these generalizations are consistent with the simple questions that we see, like the one that's on the slide. Now, of course, not every question will have this property, so you can definitely find questions where these two rules would make different predictions. So this is an example of a question with a relative clause in the subject. So here the main verb is can, and the first verb in the sentence is will. So if you learn the correct rule, you will form the question, can Maral instead will eat giggle? That's the correct question. If you learn the other rule, you will form the incorrect question, will Maral instead eat can giggle? And what Chomsky pointed out is that if you look in a corpus, those questions are extremely rare, and the child might never even come across those questions. And yet all the children generalize in the correct way and never in the incorrect way. So that's an example of the cognitive biases or constraints that children bring to the language acquisition task. Now we have tested language models basically in using Chomsky's paradigm. We trained a language model on child-directed speech and tested it on how it formed questions with a complex structure that were not necessarily seen in child-directed speech. So we gave it normal child-directed speech. So to the extent that those questions exist in that child-directed speech, the model has been exposed to them. But in practice, those are very rare in child-directed speech. So what we found is that most of the questions that the models formed, whether those were transformers or LSTMs, were the incorrect type of question, the linear question. and not the correct type of question, the hierarchical question. So this suggests that the inductive biases of transformers and LSTMs are different from the inductive biases of children, let's say. The language models that we trained are not, ChatGPT. They were trained on child-directed speech. It's a small amount of data, and they definitely don't have all the bells and whistles that the language models you can find commercially have. They are not fine-tuned on human-written text. They don't learn from human feedback, and so on. So is it not relevant that these commercially available models can probably form the questions grammatically? My perspective here, which not everyone might agree with, is that if we want to evaluate language models in a cognitively plausible way, we need to also train the language model in a cognitively plausible way. And why is that? Well, first of all, the fact that the language model is large is not in itself an issue, right? The fact that it has a lot of parameters doesn't matter so much, because the brain also has a lot of moving parts. What really matters from my perspective is that the large language models are trained on a lot more data than humans, millions times more data than humans. And the reason that matters is that most of the evaluations we care about from cognitive science and from linguistics have to do with generalization, as I just mentioned. You have a very small number of, or even no examples of the complex structure. And at test time, you need to construct it by putting together simpler structures into a more complex structure. That's called compositional generalization. And the issue when you expose a model to trillions of words is that it will have at some point seen every sentence structure that's ever been produced by a person. And therefore, it doesn't need to generalize. It doesn't need to apply the compositional rule in the way that we think a human might. So it will probably form the question correctly, but not for the same reason that a human will form the question correctly. So superficially, it will look like it behaves like a human, but underlyingly, it might perform the task in a very different way. So with large language model, the issue is not just the amount of data, but also the kinds of data that we train the language model on. So one of the things that we train language models on a lot of languages at the same time. That's very different from the way that most people learn language. It turns out that training language models on source code is really important for certain types of structural generalization. We have work exploring that effect, actually. So this is, again, very different from the way that children learn. Children are not exposed to Python code or whatever. And language models are also trained on textbooks, linguistics articles. Basically, a lot of the, in a sense, they're trained on the test set, because the observations in those linguistics articles and the textbooks are not available to a child that's learning English, for example, but they are going to be available to a language model. And in many of the more recent models, we just don't know what the language model is trained on. So we, in recent work, we've shown that how cognitively plausible the training corpus can have a pretty important effect on how the model generalizes. And it's not always in the direction that you would expect. So we actually found that structural generalization is better when you train on child-directed speech than when you train on Wikipedia. So these details are extremely important. So I just wanted to mention an evaluation paradigm that I've been kind of marginally involved in, mostly led by other people. That's the BayBLM challenge. So this is going to be a shared task at Connell 2023. There's going to be a standard training corpus and a standard set of evaluation tasks. The training corpus is 100 million word, which is approximately the amount of words that maybe someone would have been exposed to by the age of 15 or something. And the genres of the corpus are cognitively plausible, things that the child would actually learn from. And we have two settings there, one where we only where we require the language model to only learn from the corpus, and another one where you can also learn from unlimited non-linguistic data, let's say from visual input or for any other modalities. So I think that that's going to be the kind of standardizing the training corpus and having it be from the genre and size that we think is possible for human is going to make language model evaluation much more standardized and cognitively possible. That was the first part. The second part is on comparing the behavior of language models to humans in experiments. So here we are looking at behavioral measurements from human experiments, and those might be somewhat different from the idealized generalizations from linguistics. So what we, I'm going to give you just one example. So we compared the predictions that humans make during reading to the predictions that language models make. And we know from psycholinguistics that predictability plays a really central role in human language comprehension. When a word is more predictable, it will be read faster, elicit weaker neural responses, and so on. So we focus specifically on the case of syntactically complex sentences. This is an example of the garden path sentence. So there's some words in here that are very unpredictable. You start reading the sentence before the woman visited the famous doctor, and then you reach had been drinking. You realize that the structure of the sentence is completely different from what you thought. So those words are very unpredictable to humans. And they cause a pretty dramatic, sorry, that slide's out of order. They cause a pretty dramatic increase in reading times. That's what you see between the dashed lines on the right of this panel. So we measured whether language models' word predictions for these syntactically complex sentences line up with humans' word predictions. And we developed this paradigm where we estimate the effect of predictability from syntactically simple sentences. We compute how surprising the words are in the syntactically complex sentences for a language model. And then we measure what the slowdown that the language model predicts humans will experience and compare it to the slowdown humans in fact experience in reading sentences. And what we found is that there's an order of magnitude or even more of a difference between language models that we tested and the empirical human reading times. So humans find those words and syntactically complex sentences to be much, much more unpredictable than the language models do. So the language models are maybe more flexible and they're able to consider more parses of the sentences at the same time compared to humans that get really stuck in one initially relevant parse. In work that other people have done from this Yagdo and William Schuller, they found that in fact, the better language models get at predicting the next word, the worse they become at predicting human reading times. So this is, I think, a really interesting finding, and this is like a very striking inverse correlation that we're seeing here, even though it's plotted backwards because perplexity is this weird scale. But what this plot shows is that the more accurate the model is at predicting the next word, the worse it at predicting human reading times. So what this means is that the language models are becoming increasingly less human-like. And we've also shown in our work that language models have, transformer-based models in particular, have extremely good working memory capabilities, much, much better than humans do. And that's maybe not surprising because their architecture have an attention head that can literally copy words that occurred 2,000 words ago verbatim. And that's not an ability that humans have. Humans are much more limited in their working memory. So as a parenthetical, it's not really clear that for AI systems, we really want to mimic human behavior. Like one, I guess, classic example is syllogistic reasoning. So humans make a lot of mistakes in reasoning. It's like with this premise, all bakers are artists and no chemists are bakers. What can you conclude from the combination of those two sentences? Well, the answer is that what you can conclude is that some artists are not chemists. But if you give this syllogism to human participants, maybe one person in 100 will give you the right answer here. And it's not clear that that's what you want from an AI system, or that you want an AI system to have limited working memory like humans. So the second form of cognitive evaluation for AI is of maybe questionable benefit for AI. It might be useful for cognitive science though, because then you can come up with models that are more useful for cognitive modeling. So to sum up what I said, I think that cognitively evaluating language model architectures in how well they generalize only makes sense if we train them on the amount and kind of data that humans have access to. Otherwise, we're not really testing generalization anymore. It's not clear to me that we ever want to match human performance. That includes errors in reasoning or working memory limitations. But if we do want to match them, we probably also need models that are resource limited in human-like ways. So that can be in terms of their working memory or other limitations. And we have work in that direction as well. Okay, that's what I wanted to say today.
Fabulous. Thank
I
you,
will
Tal.
stop. All right.
Perfect. Yeah, so we have a couple minutes for questions.
Oh, sorry, I thought I had 15 minutes.
Oh, that's okay. It's fine. We're off script anyway at this point.
Oh, sorry. Yeah.
No, it's great. Yeah, I guess I was going to kick off the question maybe with yeah, actually, yeah, maybe we'll just do this one question just because I'm already asking it, and then save the rest for the panel at the end. But what so you've highlighted a lot of input issues that differ, but then there's kind of these like functional capacity type things, and there's that nice like resource rational Han and Roger Levy paper recently showing that like, yeah, memory accounts for some of this, right? Or that like chopping off context or something accounts for some of this. But do you have other kind of candidates like functional constraints that might be on people that are not being built into these systems?
Other than memory limitations? So for reasoning, this is specifically something that's on my mind right now because I have a project on it. There are really interesting cognitive theories of reasoning that suggest that the way that you reason about these kind of general sense of quantifier involves actually constructing a mental model with specific individuals that have the properties that the quantifiers express. And then you are limited in the number of mental models like that it can generate, and the models have various limitations that are due to these cognitive biases that humans have. I don't see huge reason to think that language models should necessarily have those limitations, but we can definitely build them into the language model. That's kind of actually an experiment that we're doing right now.
That's awesome. Yeah, so something like the beam width and something that you're maintaining, and like the set of alternatives, yeah, which may be also relevant for Jen's presentation later.